we say a collection of the vectors span Rn if every vector in Rn is a linear combination of the collection of the vectors. I will show you a particular case. Okay. Now, for instance, in R2, now let's recall R2 is the set consisting of all the vectors with two components. In R2, we have two standard basis vectors. The first one is denoted using the vector I. I is the vector with two components, 1, 0, right? And the j is the vector with two components, so 0, 1. Now we are going to use the definition to verify the two vectors I and j span R2. By that we mean we are trying to verify every vector in R2 is a linear combination of I and j. I think we have seen that many times. Okay. I just read the conclusion and why. Okay. The two vectors I and j. The two vectors they span R2. I will tell you why. So because to say two vectors they span R2, we want to verify every vector in R2 is a linear combination of I and j. So because every vector, so now let's say every vector in R2 has two components. So now let's say the two vectors, the vector has two components. So now let's say A and B. We want to show every vector is a linear combination of I and j, right? So because every vector with two components A and B is a linear combination of I and j, as I think we have seen that too many times. Any vector in R2 is a linear combination of I and j as, so now let's say AB, the two components A and B, the vector in R2 with two components A and B, okay, can be written as a linear combination of I and j as AI and then plus BJ. Okay, we have seen that many times. In general, if I give you another collection of the vectors, if I want you to show the vectors they span R2, you have to do the same thing. You have to show every vector in R2 is a linear combination of the given vectors. I will show you one particular question to illustrate what's going on. Okay. The question is to ask us to determine if these two vectors span R2 or not. These two vectors in this particular case are not I and j, right? We want to show these two vectors. We want to determine if these two vectors span R2 or not. By that we mean we want to determine if every vector in R2 is a linear combination of these two vectors. Okay, I'm going to make your life a little easier. I will talk about the shortcut method first, and then I'm going to tell you why. Okay. You look at the screen. On the screen, we have a shortcut method. So by that we mean you cannot see why, but the method is much easier. We talk about that first, and then I'm going to connect the shortcut method to why the shortcut method will work. How does that sound? We concentrate on how first, and then I'm going to tell you why. Okay. To answer the question, to answer if a given collection of the vectors they span R2 or not, you look at the shortcut method. The first thing we do is to form a matrix, so something like this, with many columns. Now let's say if you are given two vectors, you form a matrix with two columns. Every column has the components of the given vectors. I will show you what I mean in this particular question. Again, I'm using the shortcut method. Very shortly, I'm going to tell you why I will make the connection on why the method will work. Now the solution. The shortcut method, the first thing you do is to form a new matrix. The new matrix, and then you have the given vectors. You have the components of the given vectors as columns. So by that we mean you are given two vectors. You form a matrix with two columns. The two columns are, the first column has the components of the first vectors, which is 1, 2. Okay. So basically, these two components go into the first column, and then the second column. So likewise, you have 1, 1. Right? You know what's going on. The components of the components of the vector 1, 1 so go into the second column. That's what we meant by step 1. Form a matrix like that. You look at how to form the matrix. Every column has the components of v1, v2 up to vm. The second thing we do is to perform row reductions to make the matrix RREF. We perform row reductions to make the matrix into RREF. I told you when we did chapter 1, the unit 1, I mean, the technique of putting a matrix into RREF is going to be used over and over again. So later in the course, you are going to see you need to use the technique until the end of the course. Okay. Now we put the matrix into RREF. So this one is simple. Okay. We have not been doing that for quite a while, but the first thing we do is to make leading one of row 1, right? So that is the leading one of row 1, and then we use the leading one of row 1 to make the odd numbers below the leading one zeros. By that we mean we choose a multiple, we multiply row 1 by a number, and then we add the multiple to row 2. We want to make that location 0. Okay. We have seen this many times, right? We multiply row 1 by the scalar of -2 and add the multiple to row 2. Row 2 is changed. At this point, I think all of you guys have no problems with that. I will do this a little bit quicker. The first row is not changed. 1, 1, 1. I mean 1, 1. The new second row becomes 0. That's what we want. We want to make this location 0. Okay. We multiply row 1 by -2. Add the multiple to row 2. This location becomes, I think, -1. Is that right? -1. So let me know if you see anything wrong. Okay. And then we keep on going. This leading one of row 1, this location is never going to be changed anymore. Okay, so do not change that number for the rest of the operations we are going to perform. The next thing we do is to make leading one of row 2. We want to make this location 1, right? To achieve that, we multiply row 2 by a non-zero number of -1. By that we mean row 2 becomes -1 times row 2. Okay. The first row 1, 1, not changed, 0, 1, right? I circled the two leading ones, the leading one of row 1, the leading one of row 2. Okay. These numbers, these leading ones are not going to be changed anymore. So we're almost there. Now all we need is to use leading one of row 2 to make this location 0. Okay. We add -1 multiple of row 2 to row 1, right? We multiply row 2 by -1. I mean, we multiply row 2 by -1. and then we add the multiple to row 1, and then row 1 is changed. Okay. Eventually we have a matrix in RREF, so 1 0 0 1, right? After getting RREF, we can answer the question. Again, the question is, do these two vectors span R2? And then by definition, it means if every vector in R2 is a linear combination of the two given vectors. To use the shortcut method, we form a matrix like that. The components of the vectors go into the columns, right? And then we make the matrix RREF. We put the matrix into RREF using elementary row operations. Okay. I'm repeating that many times because many of you guys came in late. After getting the matrix in RREF, then we can answer the question using the shortcut method. Now you look at the statement. Okay. What we need is to check, is there a row consisting of all zeros in RREF? If there are no rows consisting of all zeros, then the answer is yes. By yes, I mean then you say the given two vectors, they do span R2. Okay. If there's a row consisting of at least, if there's at least one row consisting of all zeros, we're going to see the case later. Okay. Then the answer is no. By that we mean not every vector in R2 is a linear combination of the given vectors. In this particular case, you'll put the matrix into RREF. How do you answer the question? Yes, no? Do the given two vectors span R2? So maybe try to answer my question, please. You check the matrix in RREF. Yes. In this matrix, there are no rows consisting of all zeros, so the answer is yes. By that we mean the given two vectors, they do span R2. Okay. So can I just say they span the given two vectors, they span R2. So because there are no rows consisting of all zeros. Okay. Simple enough. The shortcut method is very simple, but again, it doesn't tell you why. Now I only use one question to make the connection, trying to show you why. So this works. Okay. Now we'll do the same question in two ways. The second way is designed to show you why the shortcut method works. I will copy this onto the next slide. Again, my intention is to show you why this thing will work using the definition. Now let's recall the definition. We say the two vectors, they span R2 if every vector is a linear combination of the two given vectors. To answer yes, you have to show every vector in R2 is a linear combination of the two given vectors. Okay. Now the solution. We try to determine. We need to determine the y side is also required. You need to know why. We need to determine if every vector so now let's say AB in R2 is a linear combination of the two given vectors. So now let's say 1, 2 and 1, 1. If the answer to that is yes, then using the definition, the given two vectors, they span R2. If the answer to that question is no, they do not span R2, right? So by that we mean, I think we learned that before, how to determine if a vector is a linear combination of the given vectors. Okay. So we need to solve the vector equation. So now let's say on the left hand side you have AB. You want to check if the vector with two components AB is a linear combination of the given two vectors. You want to see if you can find two numbers x and y such that the vector is the number x times 1, 2. That's a scalar multiplication, right? And then plus another number y times the second vector, so which is 1, 1, right? Again, to say the vector with two components AB is a linear combination of 1, 2 and 1, 1, you have to show there's at least one vector. So there are numbers x and y. I mean there are numbers x and y such that the equation is valid. We have seen that many times already, right? This will be converted to a system of two linear equations in two unknowns. The two unknowns are x and y. You treat a and b as constants. Okay. This vector equation is equivalent to the following system. The system, I'm going to run a little bit faster. I think we have seen that many times. Okay. So maybe I'm not going to run too fast. Okay. The left hand side is AB. The right hand side, you compare, you multiply the right hand side. You perform scalar multiplication and vector addition. The first component of the right hand side, I believe, is x, then plus y. The second component of the right hand side is 2x, and then plus y, right? So this vector equation is actually equivalent to a system of two linear equations in two unknowns. So which is, the first equation is x plus y equals a. The second equation is 2x plus y equals b. You compare you compare the corresponding components, you have a linear system of that. Now we need to solve the system to see if there's a solution. As long as the system has a solution, it means you have a value of x, you have a value of y satisfying the original vector equation, right? To solve the system, now let's recall what we do. To solve the system, we form the augmented matrix. The first row consists of 1, 1a, right? The first row is determined by that equation. 1 is the coefficient of x, 1 is the coefficient of x, a is the constant term. And the second row is 2x, it's 2, and then 1, right? And then b. This one is actually the augmented matrix of the system. We use the augmented matrix. We perform elementary row operations on the augmented matrix to determine if the system has a solution or not. Okay, now I'm going to make the connection right now. Now try to remember the augmented matrix in here. In particular, the numbers to the left of the bar. This part is actually called the matrix of coefficients. Now only concentrate on the matrix of coefficients. the matrix of coefficients is exactly the matrix we formed here. So do you see that? In terms of columns, you have 1, 2, 1, 1, right? In terms of columns, you have 1, 2, 1, 1. Now, to solve the system, we perform elementary row reductions. I believe you can see the operations we are going to perform is actually the same as the operations we perform in here, in this way, using the shortcut method. You could check, you can perform the same set of elementary row operations to make the matrix RREF. Okay. The RREF, the final form, I believe you can guess the final form. From here, you perform row operations. You have the matrix in row reduced echelon form, so something like that. And then you perform the same operations. You make the matrix into you make that augmented matrix into REF. I believe you can see to the left of the bar you still have this, right? You still have 1, 0, 0, 1. And for whatever thing you are going to get to the right of the bar, so to the right of the bar, these two question marks are going to be in terms of A and B. Probably I'm not going to use the two question marks. I will use a notation, so something like this. Can I use the notation, let's say f of AB? This notation is g of AB. I'm trying to say whatever numbers you get to the right of the bar, these numbers are going to be in terms of A and B. So don't worry too much about the function notations. I'm just trying to say that. Okay. To the right of the bar, you have something in terms of A and B. Okay. Now, if the matrix to the left of the bar, I mean in the RREF, in the matrix in RREF, if the matrix to the left of the bar, there are no rows consisting of all zeros. Now let's recall what conclusion we can make. Under this condition, in this case, if there are no rows consisting of all zeros to the left of the bar, then the system must have at least one solution to the system. I mean, the system has at least one solution. You see, there are no cases, so something like this. The left-hand side is 0, 0. The right-hand side is a non-zero number 4. So there are no cases like this, right? That's why this system, you look at mouse cursor, this system has at least one solution, which means there's a value of x, a value of y satisfying the vector equation of that, which means every vector in R2 is a linear combination of the two given vectors 1, 2 and 1, 1. So that makes sense now? I will write one more line, then we can see why. Okay. So the system or the system, it means the vector equation. Okay, so the vector equation has a solution, which means every vector in R2, every vector AB in R2 is a linear combination of 1, 2 and 1, 1. Okay. In the future, for most of the questions, we are going to use the shortcut method. Okay. If you do not fully understand this part, it doesn't matter. Okay, but try to understand. So this is why the shortcut method will work. Okay, we are going to do a few additional questions to illustrate how to determine if given vectors the span are n or not. So this time I think we can do a set of questions on the handout. Again, the shortcut method is simple. It's very easy, but it doesn't show you why. So they think it will work. Okay. Yeah, that's why I showed you one other question. We'll work on all these questions all at once. So maybe not all at once. One by one, please. One by one. This time you are given. Now let's concentrate on question 1 first. Okay. In question 1, you are given 3 vectors in R3. We are required to determine if the 3 vectors they span R3 or not. Okay. Using definition, we need to determine if every vector in R3 is a linear combination of the given 3 vectors or not. Okay. We concentrate on question 1 first. We use the shortcut method. Okay. To use the method, we form a matrix with all the components of the given vectors in columns. Now the first column has the components of the first vector, so which is 1, 2, 1, right? The second column has 2, 1, 0. The third column has 0, 0, 1. So probably I want you to try to perform elementary row operation for a little while. I believe this one is not too hard at all. Okay. Now I want you to perform elementary row operations to make the matrix REF row reduced echelon form. And then so maybe you can tell me the answer after you're done. So please, I'm going to give you 3 minutes to try that. Make leading one of row 1. This is already 1, so this location has leading one of row 1. Okay. And then you perform elementary row operations to make all the numbers below that leading one zeros, right? And then you keep on going, making leading one of row 2, and then using leading one of row 2 to make all the numbers below that leading one zeros. Okay. And then you make leading one of row 3, and then you go backward to make all the numbers above leading one zeros, and so on. Are you trying, or you don't bother? I told you to give you 3 minutes. I will give you 3 minutes. At least you have tried, I think. Can I show you the answer now? I mean the final form. I will assume all of you guys have no problems with that. The final form I think is Hardeep. So can you double check for me? The final form is 1, 0, 0, 0, 1, 0, 0, 0, 1. It's actually an identity matrix. So do I have this, Hardeep? Sure, thank you. Cool. So we perform elementary row operations to make the matrix into REF. The final form is actually an identity matrix. Now you look at the question. Determine if the now do they span R3? Do they span R3? in the final form in RREF, there are no rows consisting of all zeros, right? By that we mean every row is a non-zero row. This is the case. Your answer is yes. You answer yes. By that we mean you say the given vectors, they span R3. So maybe I'm going to write y. Okay. So there are no rows. There are no rows consisting of all zeros. So the given vectors, I'm not going to copy them. Okay. For question 1, you are given 3 vectors. The given vectors they do span R3. So do not lose track of the meaning. It means every vector in R3 can be written as a number times the first vector, another number times the second vector, another number times the third vector, which means every vector in R3 is a linear combination of the 3 vectors. Okay, now we work on question 2. We work on question 2. Using the shortcut method again. Okay. In this case, you are given 2 vectors. We are trying to determine if these 2 vectors can span R3 or not. Okay. Very shortly, I'm going to talk about the geometric meaning. You are given 2 vectors. Using the shortcut method, we form a matrix. The first column has the components of the first vector, 1, 2, 1. The second column has the components of 2, 1, 2, right? For this one, I can tell you the answer. I think all of you guys should have no problem with this. Okay. I will tell you the answer. Actually, I do not have to perform the operations. I can kind of see the answer. In the final form, there must be a leading one of row 1, right? If that's leading one of row 1, all the numbers below that leading one, they have to be zeros. And also there has to be a leading one of row 2. Or if there are no leading one of row 2, all other numbers are zeros. In this particular case, there's a leading one of row 2 actually. Okay. If that's a leading one of row 2, all other numbers, they have to be zeros, right? I'm trying to say there's no way if the matrix in 2 columns, if a matrix with 2 columns is in RREF, is in row reduced echelon form, there's no way for the third row to be a non-zero row. So that makes sense? So question? So do you have any questions, Karen? Mute your microphone, please, if you don't.
No, sir.
Okay, thank you. So not you. I was trying to summarize something in general. So there's no way for 2 vectors to span R3. In this particular question too, if you actually perform row reductions to make the matrix into REF, the final form is that. We'll answer question first. Okay. Do they span R3? Do the 2 vectors in question 2 span R3? No, they don't, right? So because there's a row consisting of all zeros, this is the case they do not span R3. For question 2, for the two vectors in R2, they do not span R2. They do not span R3, I mean. Okay. They do not span R3. I'm going to make two more comments. Okay. In general, there's no way for two vectors to span R. Now let me try again. In general, there are no way for two vectors in R3 to span R3. So because if we use the shortcut method, the matrix you form has to be something like that, right? The first row, the first column has three components, I mean, right? I mean, the matrix using the shortcut method, it has to be a 3x2 matrix, 3 rows and 2 columns, right? And then you want to perform elementary row operations. Your target is to make the matrix REF. If there's a leading one of row 1, leading one of row 1, it has to be here, right? If that's leading one of row 1, the two numbers below the leading one, they have to be zeros. Recall the definition of row reduced echelon form. Okay. There may or may not be a leading one of row 2. If there is a leading one of row 2, leading one of row 2, it has to be here. If that's leading one of row 2, all other numbers in the leading one column, they must be zeros, right? So there's no way for the third row to be a non-zero row. I mean, in any case, the third row has to be a row consisting of all zeros. This means the given two vectors cannot span R3, right? So just you just remember that. I'm going to summarize a conclusion. In general, we need a fact. So maybe a fact. Okay. In general, we need at least 3 vectors to span R3. I'm going to give the statement in general. Okay. We need at least n vectors to span Rn. We need at least 3 vectors to span R3, which means one vector cannot span R3, so which means two vectors cannot span R3. Sorry, I was trying to write Rn. We need at least n vectors to span Rn. I told you why. Okay. A fact like that is relevant to some true or false questions. You're going to see those questions on Friday. Okay. I was trying to make one other comment. Yeah, the other comment, I want you to show you why. So geometrically, two vectors cannot span R3. Okay. You imagine you are given two vectors. You are given two vectors in R3. The two vectors, they can be something like this. Okay. So now let's say the first vector is U, the second vector is V. Is it possible for every vector in R3 to be a linear combination of these two vectors? You think that way, okay? Now let's say you form all the linear combinations of U and V. We mentioned that on Friday. Geometrically, all the linear combinations of U and V form a plane passing through the origin. You just imagine you try to get all the linear combinations of these two given vectors U and V. Okay. All linear combinations of U and V form a plane passing through the origin if you treat all vectors as position vectors. Okay. So any vector not on that plane, any vector in R3 not on that plane is not a linear combination of U and V. So that makes sense? That's the geometric interpretation of what's going on. Why two vectors cannot span R3. Alright? That's probably enough comments for question 2. Now you look at question 3. In question 3, you're given 4 vectors. Now my intention is that it's possible for 4 vectors to span R3. Again, it's possible for more than 3 vectors to span R3. Okay. For question 3, I'm going to squeeze the solution in here. I believe it's possible. You'll form a matrix with the 4 columns, right? The first column 1, 0, 1, the second column 1, 1, 1, the third column 1, 1, 0, the fourth column 0, 1, 2. I will assume you have no problem to perform row reductions to make the matrix REF. I believe I have the final form in the notes. If you look at the notes in here, I believe that's the same matrix. Okay. The final form. I just need to memorize the last column. Negative 1, 3, negative 2. I think I got this. And then again, it should not be too hard to get the final form. After getting the final form, you see there are no rows consisting of all zeros, right? So this is the case. The given 4 vectors span R3. So the given 4 vectors they span R3. Simple enough. The shortcut is very simple, right? It's a matter of how to perform elementary operations to make the matrix REF. Any questions so far? If you don't, we're done that section. And then we move on to section 4, linear dependence and linear independence. Now concentrate. So this concept is not too simple to understand. We'll go over the definition first, okay? And then we'll use the definition to do at least one question, okay? So that you know what's going on. After that, we'll talk about a shortcut method. So there's also a shortcut method to determine if a set of the vectors are linearly dependent or independent. Okay. Okay, sorry, I'm trying to think how to make it simpler. the concept is not too simple to understand, but now let's try to use three simple vectors to understand the meaning. Okay. Now suppose you are given three vectors. So now let's use two vectors in R2 first. Okay. So maybe we use vector I in R2. The vector I in R2 has two components, 1, 0, and the vector J in R2 has two components, 0, 1. Now these are the two vectors in R2. Okay. In this case, you're given two vectors. You try to understand none of the two vectors is a linear combination of the other vector. I is not a linear combination of J. J is not a linear combination of I. In this case, we say the two vectors are linearly independent. Now let's try to understand that. I think it's not too hard to understand. It's not possible to write the vector I as a number. So now let's say a number k, so times j. It's not possible, right? It's because the second component of I is equal to 0. So there's no way to find such a number k. By that we mean I is not a linear combination of j. And likewise, j is not a linear combination of I. In this case, we say the two vectors are linearly independent. Okay. Now let's use another particular case to talk about linearly independent or linearly dependent. Okay. Now let's use the three vectors in R3. Okay. Now let's use I. In R3, the standard basis vectors are I, j, and k, right? I has three components, 1, 0, 0, and j has three components. Now let's say 0, 1, 0, 1, 0, right? And k has three components, 0, 0, 1. These are the three vectors in R3. Now you listen to me carefully. For these three vectors in R3, no vector in I, j, and k is a linear combination of two other vectors. Try to understand that. I is not a linear combination of j and k. J is not a linear combination of I and k. K is not a linear combination of I and j. In this case, we say the three vectors are linearly independent. I will show you one other particular case. How about I'm going to replace k with one other vector? Now I'm going to rewrite everything. Okay. I was trying to remove k, but I cannot select. Now let's consider the following set of the vectors. So can I use u, v, and w for the three vectors? So now let's say u is the vector, let's say 1, 0, 0. That's actually I, but now I want to use u to denote the vector. Okay. So now let's say v is the vector. So now let's say 0, 0, 1, 0. I mean 0, 1, 0. Now let's say w is the vector. Now let's say I will make up one. Okay, 2, 3, 0. Now you listen to my question. Are these three vectors linearly independent? By that you mean, is it possible for at least one vector to be a linear combination of two other vectors? I'm going to repeat my question, okay? is it possible for at least one vector to be a linear combination of two other vectors? If yes, I want you to write which vector is a linear combination as two other vectors as what? I think Kardeep got it right. W is 2u and then plus 3v. By that we mean W is a linear combination of u and v as what Kardeep told me. So W is a linear combination of u, 2u, and then plus 3v. So you see the equation is true, right? W is here. Or you perform the scalar multiplication and the vector addition on right hand side, you have W. Okay. This is the case. The given three vectors are linearly dependent. You see, W can when one of the vectors can be written as a linear combination of other vectors, this vector, for many purposes, is kind of redundant. Can I say redundant? Which means, in terms of linear combination, this vector is kind of dependent on two other vectors. So we say the set of the vectors are linearly dependent. Actually, I introduced the definition using something in here. Now you look at fact C. In this fact, you are given four statements. The four statements are equivalent. By that we mean we can use any of the four statements as the definition of linearly dependent. Okay. You look at C first. I introduce the definition using that way. Now suppose you are given a set of the vectors. If at least one of the vectors is a linear combination of other vectors, then we say the collection of the vectors are linearly dependent. Actually, it can be proved these four statements are equivalent. By that we mean you can use any of the four statements as the definition of the linearly dependence. This way it's easy to see the meaning, but it's not easy to do questions. In order it's easy to do questions, we use this one as the definition. Okay. Now I'm going to use a set of the vectors in R3 to show you how to use the definition to determine if the vectors are linearly dependent or independent. Okay. And then I'm going to show you a shortcut method. Okay. But now let's concentrate on the definition first. Okay. How about I'm going to use a particular question to show you the meaning. I will remove everything in here. I will put the definition and the question side by side so you can see what's going on. Okay. In the question, we are trying to determine if the three vectors are linearly dependent or independent. If the vectors are not linearly dependent, then we say the vectors are linearly independent. Okay. I hope it makes sense. We are going to use the definition here to form a vector equation first. Okay. You look at the definition. We are going to form a vector equation first. Again, the definition I'm going to use. You look at statement number A. Okay. I'm going to use statement A as the definition, which is equivalent to that actually. Okay. Again, so do not look at the definition here. You look at statement A. We are going to verify we are going to use statement A as the definition. In the future, we'll do the same thing. Okay. In that case, we form a vector equation for the given vectors. In this particular case, the vector equation is x1. You can imagine x1 is an unknown. Okay, x1 times the vector 1, 1 to 0, and then plus x2 times 0, 1, 0, and then plus x3 times 1, 1, 0, 3. On the right hand side, you have the zero vector. In any case, to use this statement as the definition to verify if the three vectors are linearly dependent or independent, you form a vector equation like that. Okay. And then we are trying to determine if the vector equation has a unique solution or many solutions. If the vector equation has many solutions, has infinitely many solutions, then the given vectors are linearly dependent. If the vector equation has a unique solution, has one and only one solution, then the given vectors are linearly independent. I want to repeat. This is the definition. To use the definition, we form a vector equation like that. Remember, the right-hand side is the zero vector in R3. It has three components, zeros, right? To answer the question, we solve the system. If the system has at least one solution, if the system has a unique solution, then the given vectors are linearly independent. If the system has infinitely many solutions, then the given vectors are linearly dependent. Okay. In any case, we need to solve the system. So this vector equation determines a linear system. I'm going to run a little bit faster. Okay. I think all of you guys can see what is the system of equations determined by the vector equation. The first component, it determines the first equation, which is x1, and then plus 0 times x2. I do not write that term. And then plus x3, right, equals 0. And then the second component on the left hand side determines the second equation, which is 2x1. I hope you can see what's going on. Okay, and then plus x2, and then 0 times x3. I do not write that. Okay, is equal to 0. And also you compare the third components. You have x3, so equals 0, right? Again, we need to solve the system in order to determine if the given three vectors are linearly dependent or independent. To solve the system, we form the augmented matrix. The augmented matrix is the first row is 1 0 1 1 0, right? 1 0 1 0. The second row 2 1 0 0. The third row consists of the numbers 0 0. Sorry, 3x3, right? 0 0 0 3 0. I think we mentioned before, the system in here is actually what we call a homogeneous system. A homogeneous system is a system in which all the components are zeros. Sorry, all the constants are zeros, right? Again, this is a homogeneous system because all the constants are zeros. Okay. Okay, now we perform elementary row operations. We want to make the matrix REF. I have a handy REF in the notes. I believe that's the same question. Okay. The final form in REF is just that. I'm going to copy it here to the PowerPoint. To the left of the bar, you have 100, 010, 001. Right. To the right of the bar, you have all zeros. Now, anybody want to tell me, is the system having a unique solution or many solutions? Or no solutions? There's no way for a homogeneous system to have no solutions. So this is the case, the system has one and only one solution. There are no columns to the left of the bar has leading ones. I mean, every column to the left of the bar has a leading one. So this is the case, the system has a unique solution. Okay. So the vector equation has a unique solution. Which means the vector equation does not have many solutions, which means the given vectors are linearly independent. The given vectors are linearly independent. Again, from a vector equation like that, and then you solve the equation, convert the vector equation to a system, solve the equation. Okay, if the equation has one and only one solution, if the system has a unique solution, then the given vectors are linearly independent. If the system has many solutions, then the given three vectors are linearly dependent. Fortunately, there's another shortcut method to determine if the vectors are linearly independent or dependent. The shortcut method is also included in here. You look at item number D. I will redo the question using the shortcut method. Okay. Again, I'm going to redo the question using the shortcut method. Probably I'm going to make some connection on why the method will work. You look at the shortcut method, okay? To use the shortcut method, we use the same way to form a matrix A. You put the components of the vectors in columns, okay? The solution using the shortcut method. We form a matrix the same way. The first column has the components of the vector 1 to 0. So the first column is 1 to 0. The second column is 0 1 0. The third column is the components of the third vector 1 0 3. And then we put the matrix into REF. You look at the D, okay? the condition that the given vectors are linearly dependent is not every column has a leading 1. Likewise, the condition that the given vectors are linearly independent is that in the final form, every column has a leading 1. We'll do a few questions like that, so don't worry, it's easy. In this particular case, from a matrix like that, and then we perform row reductions to make the matrix into REF. So today I'm skipping all the details how to put the matrix into REF. We did too many questions in the first unit, right? The final form is that. The final form is actually an identity matrix. Now to answer the question, to answer if the given 3 vectors are linearly dependent or independent, you check columns. Okay. Is it true that every column has a leading 1? If that is the case, then the answer is that the given vectors are linearly independent. If not every column has if it's not the case that every column has a leading 1, then the given vectors are linearly dependent. We'll answer the question first, and then I'm going to make the connection. Okay. So this is the case that every column has a leading 1. So there are 3 columns altogether, right? There are 3 columns. The first column has leading 1 of row 1. The second column has leading 1 of row 2. The third column has leading 1 of row 3. Every column has a leading 1. This is the case the given 3 vectors are linearly independent. Okay. So the given vectors kind of say they, so they are linearly independent. So because every column has a leading 1, so maybe for the first question I'm going to write down the reason. Okay. So because every column in the final form in the matrix in REF has a leading 1. For the linearly dependence and the independence, okay. Now I'm going to make the connection. I showed you the definition. The other how to use the definition to show the given vectors, the given 3 vectors are linearly independent first, and then I showed you the shortcut method. Now I'm going to make the connection. Okay. You look at that screen. Using the definition, we form an equation of 4 vectors, right? A vector equation, and then so they think it's converted to a linear system. To solve the system, we form the augmented matrix. Now I want you to look at the augmented matrix. To the left of the bar, to the left of the bar, you have exactly the matrix here. So do you see to the left of the bar for the system in the augmented matrix, you have the matrix formed by the components of the vectors. 1, 1, 2, 0 is the first column, 0, 1, 0 the second column, 1, 0, 3 the third column, right? And then after performing the same set of elementary row operations, you should have this is actually in the final form for the system, for the augmented matrix. To the left of the bar, you actually have that. So this is the matrix in REF. right? If in here every column has a leading one, every column has a leading one, then it is indeed true that the given system has a unique solution. Does that make sense? The given system has a unique solution. It means the given vectors are linearly independent. Okay. Again, I showed you why. I made the connections between the two things. One thing is the shortcut method. So the other thing is the definition. Okay. In the future, in most cases, we use the shortcut method to determine if the given vectors are linearly dependent or independent. Okay. Shortcut method is super easy. Okay. The statement of the shortcut method is in the notes. You do not have to copy this. I'm going to make some comments. Okay. So basically, I made the comments already, but I'm going to make more comments. To determine if given vectors in Rn are linearly dependent or independent, you form a matrix. So something like that. You put the components of the given vectors in columns. And then what you do is to perform elementary row operations to make the matrix into REF. After getting the matrix in REF, it's here. If every column has a leading one, then the given vectors are linearly independent. Otherwise, it means not every column has a leading one. Then the given vectors are linearly dependent. Okay. So probably I do not have to copy all the questions to the PowerPoint. We just go over something. Now in question 1, we are going to use the shortcut method. You know how to form the matrix, right? And then I assume you know how to perform elementary row operations. So GJ in here is a Gauss-Jordan elimination. You do not have to use that notation. So in the future, everything you need to do is you need to show your work, okay, how to perform row operations. I'm trying to save time. Okay. This is the case that every column has a leading one. So the three vectors are linearly independent. Now you look at the question 2. Okay. In question 2, you are given two vectors. Okay. You do the same thing. You put the components of the two vectors in columns, and then the final form, the matrix in REF, is that. Now for question 2, how do you answer question? I think the question is on the screen. So because every column has a leading one, so the given two vectors are linearly independent again, right? If every column, there are two columns, every column has a leading one, then the given vectors are linearly independent. Yeah, that's why. Okay. Okay, now look at question 3. It's kind of similar, but for question 3, I'm going to make some more comments, which might be used in next class. So in next class, we are going to combine everything, many things we have learned, into one question. For a set of vectors, we need to answer many questions. But for question 3, so this time we concentrate only on determining if the vectors are linearly dependent or independent. Okay. We do the same thing. Form a matrix with 3 rows and 4 columns. So because you have 4 vectors, right? You are given 4 vectors. So because I'm going to make more comments, I'm going to copy this into the PowerPoint. Okay, now you look at the final form. Okay. How do you answer the question? Do we have a column without leading one? We have a column without leading one. Column 4 is a column without leading one, right? So this is the case. The given 4 vectors are linearly dependent. So the answer is the given vectors are linearly dependent. Okay. They are. So can I just say they are linearly dependent? I'm going to use question 3 to make two comments actually. Okay. The first comment is that is it possible for 4 vectors in R3 to be linearly independent? I'm going to repeat my question. Is it possible for 4 vectors in R3 to be linearly independent? Again, so you are going to see true or false question using those facts. Okay. Do not answer right away. Yeah, the answer is no. I'm going to tell you why. Okay, I'm going to tell you why. In any case, if you form a matrix, so something like this, it's going to be a 4x3 matrix. I'm trying to say if you are given 4 vectors in R3, the matrix you form is a matrix with 3 rows and 4 columns, right? It's going to be something like this. I'm going to use dots to denote the components. You think about that. You imagine the final form. Okay. If you have a leading one of row 1, the location of leading one of row 1 is probably here. And then if this location has leading one of row 1, these 2 locations are zeros. Okay. And likewise, the leading one of row 2 is most likely here. If leading one of row 2 is at this location, then 2 other numbers in that leading one column are zeros. And likewise, leading one of row 3 is most likely here. It may not be necessary. If leading one of row 3 is not here, then there must be a column has then there must be a column has no leading ones, right? Now we imagine the case the matrix has the most number of leading ones. Okay. So because the matrix has 3 rows, there are at least 3. Now let me try again. Because the matrix has 3 rows, there are at most 3 leading ones. So that makes sense? So try to understand that. Each leading one must be located in some column. There are at most 3 leading ones. Every leading one is in some column. Try to understand. There's at least 1 column without leading one. So that makes sense? There's at least 1 column without leading one. Which means the given vectors, they must be linearly dependent. So that makes sense? I'm trying to say it's not possible for 4 vectors in R3 to be linearly independent. I'm going to write the fact. Okay. fact. In general, we cannot have more than n linearly independent vectors in Rn. That's one comment I want to make. Actually, using the same question, I'm going to make one other comment. I still have 3 minutes. I think I can get that done in 3 minutes. Using the final form, is it possible to write the last column as a linear combination of the first 3 columns? I was trying to ask you to write. So now let's say the vector formed by the last column, -1, 3, 3, -2. The first column is 1, 0, 1, right? So which is actually 1, 0, 0. The second column is 0, 1, 0. The last column is the third column is 0, 0, 1. Now my question was, is it possible to write the last column as a linear combination of the first 3 columns? If yes, what are the coefficients? I'm looking, so just tell me the 3 numbers. I'm looking for the 3 question marks. What are the 3 question marks? Yeah, it's -1, 3, and -2. You look at the 3 numbers in here, right? The first component, the first coefficient. The first coefficient is -1. The second coefficient is 3, right? The last coefficient is -2. You can check that equation is valid for sure, right? Now the comment I want to make is that if the last column in the final form is a linear combination of the first 3 columns as that, then you can check for the given vectors, the last vector 0, 1, 2 is also a linear combination of the first 3 vectors, the first 3 given vectors with the same coefficients. You can actually verify that. The last vector 0, 1, 2 is actually -1 times the first vector. You look at the given vectors, 1, 0, 1, and then plus 3 times the second vector, 1, 1, 1, and then minus 2 times the third vector, 0, 1, 2. You can verify that, and then I cannot tell you why. So in this class, if we have time, so in next class I'm going to tell you why. Okay, but I'm trying to say, in the final form, if the last column is a linear combination of the first 3 columns, then in the given vectors, the last vector is a linear combination of the given 3 vectors. The coefficients are the same.